Hello, this is Mr. Waters, and I'm back. Okay, so I want to continue our discussion here about properties of integrals. All right, and we're going to go over some specific ones today. And but first, before we do that, I want to take a look at this homework problem here. One of our past homework problems that I checked, it was number 6 on page 261. Okay, and then we had some struggles with this. Some people were fine with how this worked, and some people were not. So I wanted to make sure we understood how this works. Okay, and it says explain in words what the integral represents, and then give units. Right. So for number 6, it has this here. See, it's the integral from 2000 to 2004 of f of t dt, where f of t is the rate at which the world's population is growing in a year in billion people per year. So keep in mind that here's the integral right here, 2004, 2000, right, f of t dt. And keep in mind that if we could graph that, it might look, I don't know, something like this. 2000, can't really see that, can you? Okay, I'm going to slide it up here so we're getting that more in view. Here we go. And then I'll also, I think at this point I'll go ahead and I'm going to go ahead and zoom back out again because we don't have to read the problem, right? Get this back out to normal zoom, okay? Okay, so there we go, okay? So, we're supposed to interpret this integral here, okay? And keep in mind that graph-wise, it's going to look something like this, right? And this is f of t. This is the rate at which the population is growing per year, right? So that's a rate. So f of t, the units are going to be billions per year. You understand? It's like a speed. It's a speed at which the population is growing. And then, so that's this axis right here, right? It's billions per year, right? So here, and then this axis is just the number of years. So like that, so you can see right off, fraction-wise, cancels out, and we're getting billions, aren't we, right? So this, what this represent are billions of people, okay? And it's, in fact, specifically, the population growth, the amount of population added to the world over the whole 4 years. So remember that the integrals represent additions or accumulations or totals, right? And in this case, it's the total accumulated population growth for all 4 years, right? And so that would be, so we would say that this integral, that's our interpretation, our integral represents the total growth in pop growth in billions of people, really, for the years 2000 to 2004, right? Okay, and then the units, of course, would be billions of people. Okay, so that's how that works. So we want to make sure we understand kind of how that's working. Okay, now so that was that. So number 6. So what we wanted were the units, and then this interpretation represents the idea that the area under this curve is the total population increase for those 4 years. Okay, good. So that was our homework. Now what I want to get at here is, I'm going to bring up another window here. There it is. Okay, and this is going to show, this shows here a function, and it's actually it's function f1, right? And that's this line right here. It's a straight line, and in fact, let me scroll up here so you can see it. In fact, this is the function right here, 0.2x plus 5, so that's a linear function. Okay, don't worry about that other stuff. That's just more or less helping me display the function here. And then what this is showing, the red and the blue areas are areas under the curve from under limits here. Okay, so there are two limits. So the red and the blue area together are the area under the curve from A to B. And so if this is little f of t, or little f1 of x, I mean, then the area under the curve would be, you know, the total accumulated change from A to B. Now I've also designated another point in between C, and I can go ahead and I can, turns out I can move these, right, these limits, so we can change that, and then I can move this limit here, this that divides the total A to B area into two separate regions, right, a red one and a blue one, right? And then over here, I hope you can see, these are the integrals that are showing the areas under the curve. So the first thing we're seeing is this one right here, that f1 of x dx from A to B, that's a total of 49.6 units, right? Whatever the units are. So the area is 49.6 of something or other, okay? Where the F1 curve on the top, that represents the rate of change of that area. So anyway, then, so the red and the blue areas total are those together. Now, under this one here, we'll come back to that one in a minute. This one here shows this one here is showing the blue area. From C up to B, the area under the curve given by that definite integral is 32.5. And then this one here gives the area A to C. It's kind of out of order there, isn't it? But it's A to C, so this represents the definite integral, the area under the curve from A to C, which is the red area. Now what I want you to see is that the red area plus the blue area is equal to the total area. Huh. So in other words, it's one property of integrals, and it's kind of common sense, and it looks like this, okay? Back to the camera here, that if we've got, here is f, over here this is f of t, or whatever those, you know, whatever the horizontal variable is down there, then if the red area on this picture, the red area is the total area from A to B, then the green and the blue add up between the two of them together, right? It's like 2 plus 3 would be equal to 5, right? Well, formally it looks like this. This is, you know, property or characteristic number one of integrals, and that is that the integral from A to B is equal to the integral from A to C plus the integral from C to B under the conditions that, and I should write this out fair and square here so that we're clear on this, under the condition that the point C is between A and B, right? In other words, if this is true here, if here, I'll write it up here, if C is less than B, greater than A. In other words, C is a point between A and B on that interval A to B, then that area plus that area equals that area, right? Does that make sense? Okay, so that's the first one right there. Now, going back to the camera here, now, oh, by the way, a version of that, the subtraction would be true as well. This area here, C to B, would be equal to the entire area, A to B, minus the area A to C, right? So C to B is equal to A to B minus A to C, which is what this says here, okay? The integral from the area of C to B is equal to A to B minus the definite integral from A to C for f of x. And I suppose I should call that x down there. It's confusing, right? Okay, anyway, good. Now, another point, again, one which seems sensible, but we got to say it out loud here. Okay, let me get our graph back. Here it is. And that's this one here take a look here. Here is back to a to b f1 of x dx. Now I want you to notice down below that, and it may not look at first like there's any difference, but notice it's the same integral, except this, instead of from a to b, I've got the interval going from b to a. So instead of subtracting b minus a to give you the area under the curve, we're going to subtract a minus b. Well, you can see that since a is lower or less, that's going to come out negative. So in other words, the order in which we have these integration constants here, integration boundaries, makes a difference. If you want the typical positive area here, we're adding from the lower limit to the upper limit. But if we add from the upper limit back down to the lower limit, we get the opposite. And as you see here, that's negative 49.6 instead of positive 49.6. Okay? So that's an important point. So those, and that's what, let me go back here. So I hope that's pretty clear there. And it's as if you're saying, well, why? Because, I mean, it's the same area, right? Why would it make any difference whether you add from left to right or right to left? I mean, you have the same area. And in a sense, that's true. In the same sense that negative 5 and positive 5 have both got the same absolute value of 5, which is a distance from 0. But you want to keep in mind that when we're adding, if we're doing the integral, if this one here, a to b, we're adding from a up to b, right? And so we're adding in a positive direction, all right? If we go from b back to a, we're moving in a negative direction. So it's like when we had, when we talked about the area under the curve being distance, right? In one case, it was distance walking away from the house. In the other case, it was distance walking towards the house. It was the same distance, right? Absolute value-wise, but the direction was different. And that directionality, that vector quantity of directionality is given by negative. So pay attention to these constants here. If the constants are backwards from high to low, that's going to give you a negative quantity for the area. Okay, we're all right with that? Okay, cool. Now let's see. So that's one bit right there. Now, let me kind of close this down and make it neater looking. Highly related to that, all right, is going to be another situation down here. And that is, and let me open up this one here. And that is, if we are multiplying by a constant, okay? And so what I'm going to show you here, I'm going to make it bigger like this so we can see the entire thing, okay? I'm going to scroll up, show all this again, okay, down to here. Now I want to just hide that for a minute. I'm not going to try to hide everything, and hide that for a minute. Okay, so what we're looking at is this function here, j1 of x is equal to 5. Now, technically, this can be any function I want. For instance, I could make it 2x, right? And so we would be graphing, there's the green line, which is y equals 2x. But to keep this idea simple, I'm going to make it a nice constant and have it be 5, right? So there it is. So so the function y equals j1 of x is equal to 5 is the horizontal line y equals 5, and in the area under the curve from a to b is, as you see, a nice, neat, convenient rectangle, right? Okay, does that make sense? Okay. So you don't need that. Okay. So here it is. Now the area under the curve is given by 5. The interval from, I think you can see it's from 2 up to 10. So the delta t, the change in x here, that's the increase in x, that's going to be 8. And then the height is 5. So you can see that's why here it's giving the area from A to B, just length times width, it's giving the area of 40. That make sense? Okay. Now what we're going to do is I'm going to multiply this by a constant k on the inside. And it's going to be some number k, and here it is. In fact, it's equal to 2. And I can change it back and forth like that, but it's going to be equal to 2. Okay? So look what happens if I take this function here, j1 of x is equal to 5, and multiply it by 2. Well, let me go back up and show this again here so we can see the entire, so we can see the multiplied function. Here it is. We've multiplied everything by here by 2, and instead of the area being 40, we get 80, which makes sense because we're multiplying 2 inside here, right? 2 times 5 is 10, so it's 10 high, and then still 8 along, so the area is 80. Now, all I mean to tell you is simply this, that this constant, which in this case is a 2, we can, and it's just a coefficient inside the integral, you understand, we can take that and move it to the outside. And so we get k, which is 2, being multiplied on the outside of the integral. Notice that it comes out to be the same. So this is another convenient property that if we've got it like a coefficient inside of the integral, we can move it outside of the integral, and it makes it, in many cases, you'll see, might see later on, a simpler, it'll make working the integral easier if we can simplify it that way. So that's another property there. So let me go ahead here, and I'm going to hide that again to make it a little bit simpler looking because we're going to come back. And here is the camera back again, right? And then here is property number 4, which is, and I've written it right here, k times f of x dx is equal to k times f of x dx from a to b. So I've taken this k and I've slid it to the outside, right? Now we're going to do some examples of this later on, okay? And that'll be, I'm going to finish up with this hopefully quick video about some of the properties of integrals, some of the basic properties of how we combine and transform integrals, okay? And maybe you can see here that we had something similar to this with derivatives, right? And here is, I'm going to put property number 5 is just property number 1 and 2 backwards, right? That if we've got two functions adding on the inside of an integral, we can add them, we can integrate them separately with two separate integrals. And again, you'll see when we'll do a couple of examples of that where that's going to make doing the integrals in many cases a lot simpler, like it did with derivatives, okay? Now, there's one more property that I want to go over here, and then I'm going to go ahead and you'll have this sheet here, by the way, fair and square with all the properties on it. I'm going to go ahead and do some examples, but that'll be the next video, okay? So I'm going to keep going here. So that is, now I want to show you to the next one, which will be kind of the last one, okay? And this property here shows that if we are, I think of it as combining integrals horizontally, like that one and that one. If they are just basically continuations of each other, then it's the sum over the whole interval. Well, that also works vertically as well. So let's say we've got this function f here and another function g, and we graph them together, right? Well, what's the result of that? Well, and I'll show you here on our video screen here. And we're going to show you these two curves. I've shown you here's k1 of x, which is the parabola, x minus 2 quantity squared. And then there's k2 of x, which is the linear equation 2x minus 4, right? Now, what they're showing here is I've got it shaded in, is the area between the two curves, right? That is the function that is k1 of x minus k2 of x. or rather other way around, sorry, it's k2 of x minus k1 of x, because in this interval, the linear function is actually a little bit above. And so if you subtract k2 minus k1, you get this combined function here, okay? And you get the area between them, okay? So that's how that goes. And so the area, so you can get the area between, vertically between two functions by subtracting the bottom one from the top one, right? Okay, now you're asking yourself, why is this coming out negative? Because I've actually got this I've got this actually organized backwards, okay? So we're actually subtracting 1 from 2, and it's coming out to be negative, okay? All right, so that's how that goes. So that's that's embodied in this property right here. Right here. Oopsie, you're not seeing it. Here it is. All right, f of x. If you've got some integral that's f of x minus g of x, d of x, if they're combined, you can subtract them like that. And we saw something like this just previously, but you see here that works out to be the difference between them, the vertical difference between them, okay? All right, now you're saying, what's the difference between that? Mr. Waters, what's the difference between that and this one? Or rather, this one here. Okay, well, notice here that the constants, that the limits are different. This one is a to b. This one is a to c. So it's giving us this horizontal distance a to b. On this one, you need to see, and it's very important. Okay, we're totaling from a to b. So in effect, what we're doing here is, and I've got this entirely backwards here. Okay, let me get my black pen here. I've got these labeled differently, opposite ways. This would be f and this is g, right? If we integrate, if f minus g, if this is f and this is g, then it's essentially going to be the g area here minus the f area here, which gives us the area between. Turns out to be a useful operation. Now, if I had it flipped around, right, g minus f, we could still do that, but the area would come out to be negative. Okay? That would be a negative area. Okay. So here's one. Okay, so here's I'm going to do. Okay, so I'm going to save this example for later. I'm going to sign off right now. I've been talking for a while here, but I want to do some examples on the next video. I want to do some examples using the properties that'll be like your homework. Okay. All right. That is all for now.